as Ms. Mary said, we've been studying this for a few weeks, so we have a small presentation to show you guys. Cell communication is an extremely important part of how organisms work. Without the steps of cellular communication following like they're supposed to, things can go pretty wrong.
Like, we are able to communicate each day with speaking or actions. Cells cannot speak, so they have to find another way to communicate their signals with each other. They do this by signal transduction pathways. They have to be able to get their signal to another cell to create a cellular response, which helps us get through the day and helps us function. Some of these transaction ways are endocrine signaling, and endocrine signaling is when a cell communicates with other cells long distantly. It goes through the bloodstream. That is hormones that will travel through your bloodstream and get to, an example is from your brain to your stomach. That is an example of endocrine signaling. Paracrine signaling is when cells are close in proximity and they communicate. That would be like me and Sydney communicating because we're right here. That would be me sending my signal to her right here. And there's another one called autocrine signaling, and that is me communicating with myself. That is a cell communicating within itself. And the last one is synaptic signaling. And that one is where a signal is shot through a cell and there is a gap. It's called a synapse. And that is like a junction and opening that the signal has to go through and then reach the other target cell.
Today we'll be focusing on local signaling and how it affects neurofibromatosis. In neurofibromatosis, the disorder is caused by a mutation of a gene. There are actually two types of neurofibromatosis. There's NF1 and NF2. We're going to be focusing mainly on NF1 today because it's more common, and it's a result of the gene NF1 being mutated.
NF1 is on chromosome 17, and due to this, for our disease, these are the symptoms that you will see. You'll see these cafe au lait spots, and that is pretty much, it'll look like a birthmark, or some will look like freckles, some can be big, some can be medium, some can be small. It just depends on the body.
The cafe au lait spots also, whenever they appear in the eye, they're called Lisch nodules, and there are also other various types of things that happen to your eyes with this disease. It just happens to affect the eyes.
There are also neurofibromas, and that's just a big word that means tumors in our disease. It will be these spots that pop up around the body. Some can be malignant, some can be benign. Malignant means cancerous, and benign means not cancerous. And these can pop up around anywhere on the body.
Typically, they pop up on nerve cells, and so, like you said, all over the body, because your nerve cells cover literally all over your body. Another symptom includes bone defects and scoliosis, which would be underbone defects.
And then, I missed it, but this is the cafe au lait spots. As you can see, they look just like a birthmark or different freckles around the skin. Some are not even noticeable sometimes.
Okay, as you said before, NF1, the gene, is located on chromosome 17. This is the gene that causes neurofibromatosis 1. NF2, which is, like I said, less common, is on gene 22. NF2 affects 1 out of every 40,000 births, where NF1 affects 1 out of every 4,000 births. Now, NF1 is definitely the most dangerous form of neurofibromatosis because the tumors that are formed along the body are often malignant, which means that they're harmful. And NF2, there are less malignant tumors, so you're not as likely to die as earlier as you would.
Actually, the life expectancy for NF1 with the malignant tumors is around 15 years. That's just due to the cancer. If you have benign tumors, the non-malignant ones, you're going to range from about a normal lifespan.
And children have a 50% chance of inheriting neurofibromatosis from a parent that had it. And it can also lead to learning disabilities and mental problems.
Now, this whole disease is caused by one faulty mishap in our transduction pathway.
On the cell membrane, there is a phospholipid bilayer. These are just basically fats. Inside these fats, like layered in between, are proteins. This type of protein is called a receptor tyrosine. And that sounds like a bunch of smart words, but basically all it is a protein. this protein has a tail that allows ligands, which is just a fancy word for a signal, to bind to it.
In our case, the signal is a growth factor. It's just a molecule that's going to bind right here at this spot.
RTKs exist as two separate monomers before a ligand is bound to them. Whenever a ligand, however, binds to the RTK comes together and becomes in its active state. On one side of this RTK, there's an enzyme. And enzymes are biological catalysts. They speed up reactions. So what this enzyme's job is to do, it pulls off a phosphate group from ATP that has been floating along inside the cell. It pulls the phosphate group off of that and adds it to the other side of the monomer.
And this happens when ATP, as we all learn in biology, that's just an energy source. Well, in our case, it uses GTP, which is pretty much the same thing as ATP, it's another energy source. And what happens is GTP is translated to GDP, which means it loses a phosphate group. So those phosphate groups that are pulled off of GTP is what is attached to this.
Now, once the phosphate group is attached to the RTK can then activate other proteins. You have proteins all throughout your body. Your body's job is just to synthesize proteins in order for your daily life. So whenever you have your proteins floating around here and the RTK is in its active state, the relay protein is what we call them, binds to the RTK, and the RTK then attaches phosphates to those and activates them. This oftentimes causes protein cascades, which basically starts what we call an amplification effect, which means this causes it gets bigger and bigger and bigger to where the body can control many processes.
And this is what a normal working RTK would look like. You would have your active and your inactive. But in our case, as an NF, our mess up happens right here with this other protein called Neurofibromatosis and RAS. RAS is one of the relay proteins that she was talking about. RAS is the duty of that is to help your cells grow, help them develop, help them divide, and of course we all need that as we get older and we have to grow and divide. But once we reach a certain point, our cells need to stop growing, especially certain cells. They do not need to grow any longer. So that is where neurofibromatosis comes in. When RAS has reached its state where cells no longer need to grow, neurofibromatosis is supposed to come in and take a phosphate off of RAS. As she said, when a phosphate is taken off of RAS, that puts it in its inactive state, which means that the cells will no longer grow. But when neurofibromatosis is absent or it's mutated, it does not have the ability to take the phosphate off of this. This picture is a better demonstration. Here's your RAS and here's your neurofibromatosis. When your neurofibromatosis comes in, it takes it off and it is prevented. So if your cells don't grow, tumors don't grow. But as in our case, either this is absent or the neurofibromatosis is mutated. So it is not able to connect to your RAS and take that phosphate off, which means uncontrolled cell growth. And if you have uncontrolled cell growth, that is what's going to lead you to your tumors, and that is where our neurofibromas come from.
So, as we talked about today, we cannot stress how important this signal transduction pathway goes along. Without every step following smoothly, many things can go wrong inside the body. Just by that one mutated gene, tumors have shot up all over your nervous system and can even cause death in some cases, especially in NF1.
So, this is all of our research. Thank y'all for listening.
Very good. All right. Just ask some questions. Okay. First question that I have. Could you explain RAS just a little bit more to me? What its purpose is in the whole signal transduction pathway?
Alright, well, RAS, as we said before, RAS is just a relay protein. So the purpose of relay proteins in general is just to relay the transduction, to make the processes get bigger and bigger and bigger in order to create a response.
And carry out a function.
Yeah. So RAS is just the particular relay protein that deals with neurofibromatosis.
Alright, so the problem with RAS in someone with neurofibromatosis, it doesn't get inactivated?
It doesn't get its protein taken off. The problem is with neurofibromin. When neurofibromin is supposed to come in and take that phosphate off, so RAS will quit working. But if neurofibromin is mutated where it doesn't like do that lock and key fit, or it's absent in some cases, RAS is never going to be inactivated, so it just keeps on growing and keeps on growing.
And you said that these tumors can not only be superficial in our skin, but they can also be.
They can be anywhere along the nervous system. They can be in or under the skin. And NF2, we didn't mention this, but in NF2, they're more commonly found in the ear. NF2 basically just deals with like Schwann cells around, which is like the insulation around nerve cells. Whenever the tumors grow along those in NF2.
So, and one of the things that we talk about a lot with cell communication is the amplification of these signals. You start with something small, and then by the time that reaction goes on, you have a big response compared to a small little signal. So how is this an example of amplification?
You start, okay, well, and there's a good part of it, and then there's a bad part of it. Well, you start with that one RAS, and as we've learned, cells, that one RAS can cause several other transductions to amplify. So if that one RAS cell can cause several different cells to grow and divide.
And so basically that one RAS affects multiple cells.
So exactly, if it's not inactivated, it's not just affecting one cell to keep growing. It's affecting several different cells to keep growing.
You need RAS in order for your body to grow on a normal daily basis, but too much of this protein can cause you to grow the tumors.
So everybody in here has RAS.
Everyone in here has a functioning, yeah, we forgot to mention that. Everyone in here has this functioning system that we mentioned earlier. You have RAS, you have neurofibromin, you have the gene NF1, but the difference between you and someone with neurofibromatosis is that your